So just a reminder that Lab 1 is due a week from today at midnight. I encourage everybody to take at least a quick look at it sometime before this weekend or during the weekend, so that you're not caught with a last minute, oh my goodness, this is going to take me longer than I thought. So at least you're doing a sin of commission rather than a sin of omission. So please do that. Feel free to post any questions you have about the lab on Piazza. If you have a question about your particular circuit that you're doing, you can post a private question to the staff on Piazza. If you do that, if you post so that we know who you are, we can actually pull up your design, the one that's saved in the online system. We can pull it up and look at it for you. If you post anonymously, we're not able to give quite so specific a help. So today, we're going to look into actually how to build combinational logic gates that satisfy all the criteria that we set out last time. So let's just remind ourselves what we wanted out of a combinational device. We developed as our digital signaling specification 4 voltage thresholds, 2 thresholds for the input, and basically any voltage below VIL should be treated by our circuitry as representing a bit of 0. Any voltage greater than VIH on an input should be treated by our circuitry as representing a 1 or a logic high. Similarly, on the outputs, we had 2 output specifications that if you want to build your device to output a 0, it must output a voltage below VOL, and if it's going to output a 1, it must output a voltage above VOH. And so those are 4 separate voltage specifications, and in fact, they're separated on the number line, or they're on the number line like so. So first we have VOL and then VIL. And this is one of the 2 noise margins. And then we have VIH and VOH. And this is the other. This is the high noise margin. So the noise margin tells us how much an output voltage can be corrupted on its way to the next input and still be treated as a correct encoding of whatever bit you were trying to send, 0 or 1. When we put all those together, and we said, well, look, I'm going to make a plot of, I'm going to take a device, in this case an inverter, so this is different than the one we saw at the last lecture. An inverter, if you put in a 0, you get out a 1, and if you put in a 1, you get out a 0. It inverts the bit that you're putting in. So if I put in a low voltage, I get out a high voltage. So anything below VIL produces a voltage above VIH, or VOH. And then the same thing if I put in a low voltage, if I put in a high voltage, I get out a low voltage. Okay, and so if we look at this, we discover, remember that this region is narrower than it is high. In other words, the distance between VOL and VOH is greater than the distance between VIL and VIH. That sort of falls right out of looking at the number line arrangement. And that was important to us because that meant we had to figure out how to build combinational logic that had gain. In other words, to get through this region, there has to be at least one part of the device curve here that if I make a little change in V in, I get a much bigger change in V out. That's the only way in which I'm going to be able to squeeze my transfer curve through this narrow region in the middle. And you can see sort of self-evidently it has to be nonlinear. In other words, it has to have a different gain depending on the input voltage. So low and high input voltages, you can see there's relatively low gain. A small change in the input produces almost no change in the output voltage. So there's no amplification there. And in the middle, there's very high gain. So a device that changes gain throughout its input range is a device that we call nonlinear. So this is a nonlinear device with a gain greater than 1. Lots of gain is good. In fact, if you were going to draw the ideal voltage transfer curve, okay, ideal in the sense of providing the biggest noise margins, what would the ideal voltage transfer curve look like? Yeah, so usually everybody's sort of doing this strange incantation. This looks like I'm at Hogwarts here. What does this one do, Professor? Okay, so the answer is the ideal voltage transfer curve, so V in on this axis and V out on this axis, would look something like this, right, where this would be at the power supply. So VOH and VOL could basically be at the power supply and ground, and then VIH and VIL could be very close to the middle. And so that means I've maximized the distance between VIL and VOL and VOH and VIH, and that will give me the best possible noise margins. So if we could wish for any device that we wanted, we would wish for one where that was the voltage transfer curve. And you know, through the miracle of modern electronics, we are going to get our wish, or very, very close to it. Okay, of course we want them cheap and small. We're looking for devices that we can manufacture in large volumes for not much money. We'll see that today. The device that is the key to this technology is called a MOSFET, a metal oxide semiconductor field effect transistor. We'll meet Mr. MOSFET in the next slide. We build between around 10 to the 22nd of those devices every year. So that's the thing. Think of all the things mankind manufactures, MOSFETs rank high up on the list of things we build a lot of. For very little money, so that's good. You can buy billions and billions of MOSFETs for a handful of dollars. We understand that if we change the input voltage, the output voltage needs to change, and to basically charge and discharge the capacitance, the nodal capacitance on the output node. That means in order to change its voltage, to have it reflect the new output value, we're going to have to dissipate some power to do that. So that's called the dynamic power of the device, the power that we have to spend, and we always have to spend it, in order to change the voltage on an electrical node. Okay. What we really hope for is that if we're not changing any voltages in our circuit, if our circuit is quiescent, that in fact we're spending zero power. So we hope that we'll come up with a technology that will do that. And finally, we're interested in what operations do we want to perform. So far we've seen buffer and inverter. Clearly we're going to need a richer repertoire of logic functions in order to build computers and other interesting digital systems. So here's a picture of a MOSFET. So just to give you a sense, nowadays the dimension that I'm just outlining here that goes across that red cross section, that dimension is very, very, very small now. Okay, so it tends to be, we're talking about 14 nanometers, I think is sort of the current state of the art. So just to give you a sense, nanometers, everybody says, oh, fine, I know what a nanometer is. But just to be clear, what is the wavelength of, say, red light in nanometers? Anyone know offhand? Well, 600 for red. Yeah, okay. So, 400 is more blue. So 600 nanometers for red. And so we're talking about things that are very, very, very small fraction of the wavelength of light. Okay, and that means that if I said, here, come look at it under my optical microscope, being the physicist you are, you'd all laugh merrily and say, oh, that's way below the Rayleigh limit of an optical microscope. So the only way we can see these things is very high technology electron microscopes. So we're building things that are, 14 nanometers is 140 angstroms. We're building things that are almost molecular scale these days to perform our electronics. Not quite. So this device, this MOSFET device, we're going to treat it as a switch. And what the switch is, so the thing that the electrical node that controls the switch is a voltage controlled switch, is the gate node. So this polysilicon wire that you see here is the gate node of the device. That's the thing that will control the switch. And depending on the voltage of the gate node, we will either make a connection between these two nodes called the source and drain, okay, or we won't. So we're basically building a very, very, very tiny voltage-controlled switch. That's what our goal, that's what this device is, this MOSFET. Now that's a very simplified model. The actual electrical model for a MOSFET is much more complicated. If you're interested, you can take 6002. But if we use it according to a very particular set of rules, the switch model is perfectly good for us. It will let us design logic. But if you break our rules, then our switch model behavior no longer applies, and strange things will happen to your circuitry. So, if you want a simple model, you have to obey our construction rules. So let's just talk a little bit. So the critical dimensions of a MOSFET are its length, the channel length here. So current is flowing from the drain to the source, and it goes across the length of the device. And there's some amount of resistance in that voltage controlled switch. So when the switch is conducting, if you make the switch have a longer, bigger L, a so-called longer channel, the switch will have more resistance and will basically conduct less current for a given voltage across the switch. Alrighty, so we tentatively want to make L as small as possible, and if I tell you that, you read in the Intel literature that they're building, devices on a 14 nanometer process, the 14 nanometers or the 22 nanometers or whatever it is they're telling you, that's that dimension right there. That's the dimension they're telling you, the minimum width of the device. And that dimension has been shrinking for the last, almost 50 years, so-called Moore's law. That dimension has been shrinking on a regular progression. When I first started doing this, we were talking about devices that were 250 nanometers. Okay, so things have gotten a lot smaller and a lot faster, and they use a lot less power now than they used to. The other dimension is the width. And so the way we control the performance of our voltage controlled switch, if we need to conduct a lot of current because we want the output node of our logic gate to switch quickly, so we want to suck it, produce a lot of current or suck a lot of current out, what we do is we basically make the switch wider. So the current through our voltage controlled switch is proportional to its width over its length. The length we put as small as possible because we almost never want to conduct less current. And then we choose the width for whatever speed that we want. So MOS stands for metal oxide semiconductor field effect transistor. So the metal oxide semiconductor refers to this little sandwich here, which it used to be originally the gates were made out of a metal instead of polysilicon like you see here. There's a small layer of oxide, an insulator. Here's silicon dioxide. And then below it is another plate of the capacitor. So this is basically a little capacitor, a little MOS sandwich, metal oxide semiconductor. So MOS is telling you about the, if you will, the control structure that turns this into a voltage controlled switch. And field effect transistor describes how the device works. So here's a cross section of the device. And as I say, the critical voltage that we want to consider here, the thing that changes how the device operates, has to do with the relative voltage of the gate node, that red wire, to the source terminal. So when that's below a certain, in the case of this N-channel MOSFET that we're looking at here, when that's below, in our case, about half a volt, the switch is off, it's not conducting. And what happens is that with basically not much charge on the upper plate of the capacitor, there's a little region here of non-conducting material, okay, that forms at the junction of the P device, of the substrate material with the source and drain material. And so that serves as an insulator, so there's no electrical connection here. Now what happens is we slowly add electrons to the gate. As the voltage of the gate, or as we slowly add more voltage to the gate, we're increasing the potential across the capacitor, and we're beginning to start pulling harder and harder and harder on the valence electrons, okay, of the material that's at the bottom plate of the capacitor. And eventually, and it's sort of this almost seemingly instantaneous, although if you look really closely, it's exponential, seemingly instantaneous switch that once I get a certain voltage here, right around half a volt, I suddenly am sucking all these transistors out of the valence band, all these electrons out of the valence band of the material in the substrate and moving them into the conduction band. So I'm creating mobile carriers by putting an electric field across the device. So the reason that this is a semiconductor is it conducts if you put enough electric field across it to basically create mobile carriers where there were none before. You suddenly turn it into a conductor. And that's what's happened here. Now I actually have an electrical connection called the channel between the source and drain nodes. And if I have a voltage difference now between the drain and the source, then in fact we'll get current flowing across our switch. So below half a volt VGS, the voltage of the gate relative to the source, there's no conduction. Above half a volt, there's conduction. And then as VGS gets bigger and bigger and bigger, this channel gets deeper and deeper and deeper, and we get more and more current. Okay, and everything is great. So now let's say, okay, I've got a channel. Now let's see what happens when I change the voltage across the drain and the source. Now I want to get a voltage potential across the switch and get current flowing through the switch. Everything is great, but as the difference in the voltage gets larger, what we discover is our channel, instead of just being this nice little layer of conduction, starts to go away at one end. Now, you can take a whole course, 6012, which is all about microelectronic devices, and you'll learn all about all of the effects of these electric fields on this particular semiconductor material. But what happens is that we enter a region where increasing voltage stops giving us increasing current, and the current levels off. Right? So for a while, this guy looks just like a resistor, bigger voltage across it, more current through it. But after you get to a certain voltage across the device, the VDS voltage, then in fact that current levels off and doesn't get any bigger. So if we look at this picture, this is a plot. So this is the voltage across the drain and the source, okay? And I'm looking now at the current flowing across my switch, right? That's what this plot shows. And it shows this plot for different VGS values. And so basically when the threshold is half a volt, when VGS is half a volt or less, we get all these curves right along the bottom. No current is flowing. The switch is not conducting. After we get above the threshold, increasing VDS gives us more current. Okay, but you can see that for a given VGS, so I picked this top blue curve, that's the sort of maximum VGS we can get, then when VDS is small compared to VGS, it looks like a resistor. In other words, a resistor on this sort of plot shows up as a straight line. The current through the device is linearly proportional to the voltage across the device. That's Ohm's law. So we call it ohmic or linear. But then at some point it gets saturated and we don't get more current. Okay, that's more than you probably wanted to know about MOSFETs. It's more than you need to know for most purposes in this course. The real key that we want you to know is that when VGS is small for an N-channel MOSFET, the switch is off. When we put that voltage high enough, the switch turns on. So we have a voltage-controlled switch. So now we're going to talk about how to use those voltage-controlled switches to build logic. Okay. So we actually have two flavors of voltage-controlled switch. This is the schematic diagram for, this is how we would draw it in a diagram, a schematic showing how to connect up MOSFETs to make logic gates. We'll use this symbol here, this sort of big rectangular bump between the drain and the source with the gate node here. So think of this as a picture of a little capacitor. So that's the MOS part of the MOSFET. So this is an N-channel MOSFET. So when VGS is above the threshold, this guy you can think of as a switch. We actually have a different type of voltage control switch called a P-channel MOSFET, where all the materials, we've just flipped all the different types of the semiconductor materials around. And this switch is on when VGS is below the threshold. Okay, so typically for a particular value at VGS, this switch, one of these switches will be on and the other one will be off. So these are so-called complementary switches. For a particular voltage on the gate node, in the way that we hook things up in our circuitry, for a particular voltage on the gate node, typically only one of these two switches will be on and the other will be off. And we're going to use that complementary behavior, sort of the opposite behavior, of the switches to build logic. And it's actually a very simple recipe. So let me see if I can show you that. We are going to build circuitry that has a very simple meta plan. So we have a power supply up here. So this is typically in a modern circuit around 1 volt is your power supply for the MOSFETs. Down here we're going to have 0 volts or ground. We're going to have an output node. So this is the output of our logic gate, whatever it is. And in this region here, we're going to build 2 little circuits. Okay. We're going to build a circuit called the pull-up, which is controlled by the inputs to the device. And when we want the output node to be a 1, so when we want the output node to be a 1, we're going to arrange for this circuitry in here to make a connection, use our switches to make a connection between the output node and the power supply. That's how we're going to get that node to go high. And if we want the output node to be a 0, a low voltage, we're going to make sure there's no connection up here. And instead, we're going to use our switches to make a connection to the ground power supply. So we have these little switch networks whose job it is to connect the output node of each logic gate to the power supply voltage when we want it to output to be 1, and low voltage when we and connect it to ground when we want the output to be 0. The rules that we have in order for our very simple model to work is that we only use N devices in the pull down and we only use P devices in the pull up. If you violate that rule, then our very simple model won't tell you what happens. And typically is not what your CMOS circuits pretty much follow this rule. P-channel MOSFETs up here in the pull up, N-channel MOSFETs in the pull down. Okay. So let's look at our first circuit. This is a very simple device. This is actually a transistor schematic for an inverter. Right? So this is a device that when I put in a low voltage, I get out a high voltage. The output node is high. And when the gate voltage is high, I get a low output voltage. So let's see how this works. First of all, what I can do is I can actually, set up this experiment and run it. In fact, you do that in lab 1. You actually use our little circuit simulator to figure out how this circuit works. But let's conceptually think about what's happening. In this region here, when the input voltage is low, what happens is that the pull-up is on, because remember, when the gate voltage is low on a P-channel MOSFET, it's on, and when the gate voltage is low on an N-channel MOSFET, it's off. So the P-FET is on, the N-FET is off. We have a switch now connecting the output node to the power supply. So we expect the output node basically to charge up until it reaches VDD, at which point it's done. Or in this case, 1 volt. It gets to this voltage, and now the output node and the power supply have the same voltage. There's no current flowing through the pull-up anymore, so because there's no voltage across the pull-up switches. So that means we're not dissipating power anymore. Nothing's changing. And we have a 1 on the output if we have a 0 on our single input node. And the same argument holds for the N-FET, when the voltage is high. In that case, the P-FET is off and the N-FET is on, and the output is pulled down. Okay, and in the middle, and it's actually fun to spend a while figuring this out. In the middle, what happens is they're both on, but the device actually, and that happens briefly in each transition. Every time you change the input from low to high or high to low, there's a brief moment when both of the devices are on before the switches get settled out. Anyway, in that brief moment, the device exhibits very, very high gain. Okay, and so we get almost our perfect transfer curve there. So CMOS is a logic family with excellent noise margins. Okay, so the things to remember so far are voltage-controlled switches of 2 flavors, N-channel switches, or N-FETs, which are switches that are on when the gate voltage is high, and P-channel switches, or P-FETs, which are on when the gate voltage is low. We have this set of rules. Only P switches in the pull-up, only N switches in the pull-down. Okay, and when we do that, we create a logic family which gives us, our heart's desire. Right, so, so the other thing you should remember, if you can't remember the details of the goodness, at least remember that, those of us who are in the logic business, think that CMOS is really what's made the digital revolution happen. The reason we can carry everything around in our pocket has to do with the excellent noise margins and the pretty much close to 0 static power dissipation. Now, if you've been reading the press, you understand that as our devices have gotten smaller, there's been some challenges keeping all of the wonderful things about CMOS to be true, particularly the static power dissipation. And engineers around the world have worked hard at solving some of those problems. And when we get to lecture 8, I'll tell you a bit more about some of the things that have happened in the last 5 years that have made MOSFETs continue to get smaller but still maintain all of their wonderful properties. So everybody get the basic recipe? Voltage, little switch networks, you can think of them as switch networks, okay, that control whether the output node is connected to the power supply or to ground. So that determines the output node's value. Those switches are controlled by the voltages on the input nodes to our logic gate. And we're going to arrange it so that these two switch networks are complementary. In other words, we designed the switch network so that if there's supposed to be a pull-up path, there's not a pull-down path, and vice versa. So if one switching network is on, the other switching network is off. That's what it means to be complementary. That's why it's called CMOS. Because we designed the circuitry so that there's either you get a connection to power or a connection to ground. What would happen, by the way, if you designed something where they were both on? Get something in the middle, you get, yeah.
Get a short circuit.
Right, so that would mean that we couldn't tell a lot about what the output node value is. So certainly from a logic standpoint, that would be not such a good thing. There's also another bad side effect of short circuits. I'm sorry? Fire? Yes, fires. We get, you see pictures of smoking 777s on the runway because some battery has short-circuited out. Anyway, and these things get very hot, right? And in fact, sometimes in 111, which is the digital Introduction to Digital Systems lab, people, wire up their logic circuits backwards, and all of a sudden you start seeing these plastic packages bubbling, and they go, "Wow!" And you go, "Yeah, don't touch it." And you go, "Wow!" And they say, "I didn't realize it conducted that much current." And I said, "Well, not for long." I mean, so it's. So yeah, short circuits are sort of a really bad idea on pretty much every front. So we avoid those in our basic design. Okay, so here's that recipe I talked about: complementary pull-up and pull-down circuits. If the pull-up is on and the pull-down is off, the output will be a 1 because we will have made an electrical connection between the output node and the power supply, which will cause the power supply node to be charged up until we get the output node voltage all the way to the power supply voltage. Vice versa, if it's the pull-up is off and the pull-down is on, we get a 0. If they're both on, we just talked about that. We get an unknown value on the output, but more importantly, you suddenly take your device out of your pocket and throw it across the room because it's gotten very, very hot. So not a good plan. What happens if they're both off? What can you tell me about the voltage on the output node when both of these are off? Well, suppose this guy was off and this guy was on, and I had charged this guy up, and then I turned off this guy. So that the node had gotten charged up. It's just like a little capacitor sitting out there. But now I'm no longer charging it up. What would I expect to happen to that capacitance in that node? Yeah? It would decay, but probably pretty slowly. So over brief periods of time, we can use that effect to build a memory. We can remember, if you will, whether a bit was 0 or 1, and it's on the order of milliseconds. Right, so there's a whole family of memory devices, of which we buy many of them, called DRAMs, dynamic RAMs, and they actually use this notion of a floating capacitor to save your bits, but they can only save them for about 10 milliseconds before you better read out that bit and rewrite it. Otherwise, it'll eventually enough leakage happens that we lose track of what the voltage on the capacitor here was. So we can use it as a memory, and in 3 or 4 lectures we'll come back and start building memories and talk a bit more about that. Okay, CMOS pickup lines, right? What a nice VOL you have. Okay, so the idea is a complement in this case is not with an I, meaning something you'd say to somebody you wanted to impress, but in this case with an E, which means they behave in a complementary or opposite fashion. So the NFETs and PFETs are complementary because when A is high, this device conducts. We get a connection across the switch here. This one only conducts when A is low. In other words, if A is true, this guy conducts and this guy doesn't. And when A is false or 0 or a low voltage, this guy conducts and that guy doesn't. So when one conducts, the other isn't. That's what we mean by complements. What about more complicated circuits? Here's 2 NFETs in series. So when do I get a connection between the top node and the bottom node? When does that happen? What can you tell me about the logic values on A and B to make sure that we have a connection between the top source and the bottom drain? They both have to be high, right? I mean, A has to be high and B has to be high. In other words, to find a path through both switches in series, we need to make sure that each switch itself is conducting, right? So this is, if you will, a little logic network that's performing the AND of two input values. Right? This guy conducts only when A is high and B is high. The complementary circuit is two P FETs in parallel. Okay, and this guy conducts, okay, when A is low or when B is low. Right? So you can see that if this guy is conducting, this guy isn't, and if this guy is conducting, if either A is low or B is low, then there is no path through this circuit. So those are complementary circuits themselves. And finally, we have parallel N FETs and series P FETs, and that's the other form of complement. So this is all sort of zipping by a little fast. What we're going to do is actually draw a couple of gate schematics, and that'll give you a better sense of how we're going to use these complementary properties to actually build logic gates, to build combinational devices. Okay, remember how you'd come into math class when you were in third grade, and there'd be the map of Africa would be pulled down across the blackboard? And you go, why do we have the map of Africa in math class? And then the teacher would go, doop, and then you discover there was a pop quiz she had written under the map, right? So nowadays, with PowerPoint, we can just do a pop quiz directly. So we want to figure out how this logic gate works. So it has series N FETs and parallel P FETs. Okay, so this is a combinational device. Here's the beginnings of a truth table. We have two inputs, A and B. So that means I want to look at all possible logical combinations for digital values for A and B. So 0001, 1011. For each combination, I want to figure out the value that the output node will get eventually. We give it enough time to change. So when both A and B are low, what can you tell me about the switches in that circuit? Well, when A is low, this guy switches on. So we do have a pull-up path through that P FET. This node is now connected. When A is 0, this guy is connected to VDD. Everybody with me on that? Right? And in fact, when A is low, one of the two series N FETs is off. That switch is off, so we have no pull-down path. Right? So this output value here will be 1. And in fact, if I then go through each of the other possible combinations of A and B values and figure out which FETs are on and which FETs are off, and whether the node is hence pulled up or pulled down, I'll end up with this diagram, this truth table, which is actually a well-known logic function. Well, maybe not to you, but in 2 weeks, it'll be very well known to you. It's called NAND, not AND. So this is basically the inversion of the AND. So NAND is basically 0 when both inputs are high, otherwise it's 1. Does everybody sort of follow how I did that? If you actually, so you should be able to take a transistor diagram of a CMOS gate and go make a truth table and tell me what the truth table is. And then after a while, you'll quickly recognize those truth tables as having particular names. Okay, if I actually thought about how I would build this in a semiconductor device, this is actually looking down from above, sort of if I was on a tiny little airplane flying over an integrated circuit. I would look down and find these big red wires, which are the gates, the control nodes of the MOSFETs. These are the two P FETs, these are the two N FETs. This whole device here is I've done it sort of symbolically in terms of a critical dimension called lambda, and lambda currently in the modern, so 1 lambda is basically the distance across that little red wire. So this particular implementation of a 2-input NAND gate is 16 lambda by 82 lambda. It's very small, very, very small. I can get approximately 2 to the 10th of such things. So nowadays we manufacture integrated circuits on these 12-inch, 300-millimeter wafers. That's what you see going through the manufacturing lines often these days in Asia, which is where a lot of the big manufacturing lines are, or in Intel up in the Intel fabs, like up in the Northwest. This is an older process. This is several generations old, but it costs me about $3,500 to completely process a wafer. I get about 2 to the 10th NAND gates on a wafer. That means that my actual cost for each NAND gate is about 130 nanosecents. And as I say, this has probably dropped by a couple factors of 2 since I did these numbers. Okay, so we could all pool. We could all take out a penny, and we could end up buying ourselves, billions and billions of logic gates, right? So these are not expensive devices. They're quite small. That's pretty neat. Yeah?
What does the notation with the fractions mean in the schematic?
These have to do, so when I talked about the width and length, what I did was I expressed that, I sort of wrote that as W over L as a fraction because it's really that ratio that controls the current through the device. I'm writing the width and length here. Typically, I've written this as a scaled number. In other words, 1 is the smallest possible length, and that changes it for each generation of technology. But I'll keep calling it 1 just sort of symbolically in my diagrams. So this is an N-channel MOSFET that's 4 times as long as it is wide. So good question. Other questions about these little schematics? They're big schematics, but little devices. Cute little stuff. So these guys, so this logic gate here in a modern process will produce its answer in a few picoseconds. A few picoseconds after you put so how long is a picosecond? Okay, how long does it take light to travel this distance in picoseconds? It takes 1,000 picoseconds for light to travel this distance, nanosecond a foot. Right? So we're talking a very, very short period of time. The reason that you all own umpteen gigahertz processors is that they're made of logic gates. Okay, 1 gigahertz corresponds to a 1 nanosecond cycle time. So we're talking about logic gates that are thousandths or a hundredth of that cycle time. So these are very fast, very small devices. And those are related, right? Because if they're small, the capacitance is small. That means that we can change the node voltages very, very quickly. So 10 picoseconds, right? So cheap, small, fast. This is like perfect. I'm in love again. So, sorry. Okay, so our general recipe is I have some logic function. So either I have a truth table or I actually have a Boolean expression. And we'll talk more about this next time. That tells us what I want to do. What I will do, if the gods are with me, the logic expression I want to implement can be implemented as a single pull-up network and a single pull-down network. This particular logic function can. So f is not A or not B and not C. I can draw that directly as a series parallel connections of PFETs. So when A is low or when B and C are both low, okay, I get a conduction path, so the output will be high. I then go through and replace NFETs with PFETs and series with parallel, and I come up with the corresponding complementary pull-down chain, and I glue them together, and I get a CMOS gate. Right? These I now have a complementary pull-up and pull-down network. I now have a gate that costs a few nanosecents to build and runs very quickly, and I can be billions and billions of those. So the rest of it is designing a computer is a small matter of figuring out the logic equations for what you want of the circuitry to do, and we'll have some fun doing that. We have a few more building blocks to put together first. Does this always work? Can every logic function I can think of, can I build as a single CMOS gate? And the answer, no, sadly. So it turns out that CMOS circuits are what we call naturally inverting. The only logic functions I can build are what I would characterize as an inverting logic function. And an inverting logic function is a function where if an input goes from 0 to 1, the output, if it changes at all, will go from 1 to 0. In other words, rising inputs lead to falling outputs and vice versa. That's what an inverting logic function is. Something's changing, going going high on the input, that means the output, if it changes, will go low. Those are the sorts of gates we can build with CMOS. If we want gates that if a rising input leads to a rising output, we have to build the inverting gate followed by an inverter to turn it into a non-inverting gate. So only inverting logic in CMOS. So this slide is basically all about that, something to look into. Basically in a CMOS gate, a corollary of that is in a CMOS gate, if all the inputs are 0, right, all the P FETs are on, all the N FETs are off, and the output will be high. And if all the inputs are 1, all the N FETs are on, all the P FETs are off, and the output will be low. So if you look at a truth table, you can look at the first row and the last row, and if they're 1 and 0, you know at least from looking at the first those two lines of the truth table that we're on the road to maybe this is potentially could be implemented as a CMOS gate. Okay. All right. So we've talked about roughly our little recipe for how to throw together voltage-controlled switches. These are a lot of fun, by the way. I love these little puzzles of designing. To me, designing, and you get a chance to build some logic gates in Lab 1. You'll actually even design a little library of logic gates that you'll use to implement an addition circuit. Those are fun. Sure, you can Google for the answer and just type it in and not learn anything, but it's actually fun to say, okay, how do I arrange N FETs and P FETs to get an AND gate, a NAND gate, or a NOR gate, or an XOR gate, or all the gates that I want? And so it's sort of fun to puzzle through how that would work. It's a cute puzzle. So we've talked about functionality. Let's talk a little bit about timing. I said these gates are very fast. How do we actually measure the performance of a gate? And so what I want to do is say, look, here's the gate that we're measuring. Out here. So this is the an inverter with a P channel pull up and a N channel pull down, or maybe it's a more complicated circuit, but whatever it is, it's a CMOS gate. Out here we have some other gates, downstream gates, that are representing the capacitive load. In other words, the things that are going to end up slowing down how quickly this node can change. So there's some resistance to capacitor in the wire that connects the output of one gate to the input of the next. Plus the little capacitors here in the MOS part of the MOSFET structure themselves add some capacitance. And so as I try to charge and discharge the output of a particular logic gate, the capacitance that I have to charge and discharge comes partly from the wires and partly from the MOSFETs in the gates that I'm connecting to. So things aren't going to happen instantaneously. You get pictures that look like this. If I make the input go through something approximating a step, I'll find the output node looks like an RC time constant discharge. Right? I've basically made a path to ground. When this went high, I made a path to ground. So I'm discharging all of the capacitance here, which had been high. See, that node was high, had a high voltage, and now I'm discharging it, it looks like an RC circuit. I'm slowly discharging it, and when I'm done, it's low. And the way I make my measurements is I start being very, very careful. So everybody get that? So when you actually look at voltage waveforms for these things, you'll see that they look like RC time constants. So the R is the effective resistance and the C is the effective load capacitance. And so the time it takes for a node to change can be characterized by that little RC time constant. And that's everything we want from 802. Okay. And if you didn't take 802 and you say, God, this electric stuff is confusing me, Chris, just remember that by making wider MOSFETs, by making the W number bigger, you're making the R smaller, and so that means that the RC time constant is smaller, which means the node will change more quickly. That makes sense? Okay. Alrighty, so how do we do the measurements? Here I'm being very careful. I'm looking at when the input node becomes valid. So the input node becomes valid when it crosses the VIH threshold. That's when it's suddenly now a legal 1. And I'm going to measure the time it takes for the output node to cross VOL, which is the output low threshold. And I'm going to characterize that timing measurement as with a single number. So you can actually see there's two measurements I'll take, one for a rising transition input and one for a falling input. And in both cases, I'm going to come up with a single number that is an upper bound in all of these measurements. And the upper bound we call the propagation delay of the gate. That's that magic number that tells us how fast a gate is. So we look at all the different ways in which the gate changes its output value depending on the combinations of input. We test all of those transitions and we make measurements on the gate, and then for engineering purposes we tell you give you an upper bound on all those measurements. The TPD of the gate, the propagation delay of a gate, TPD is propagation delay. TPD is basically telling you, okay, how long you have to wait after the input changes before the output is guaranteed to reflect the new value of the inputs. I've changed the inputs. How long do I have to wait before the output has the right value on it? That's the propagation delay. And as I say, in modern circuits, that's on the order of a handful of picoseconds. Okay. Occasionally, it's useful to measure one other number, which is though I'm starting to change the input. So here I'm looking at the same rising and falling input transitions, but here, this is the magic point at which the input becomes invalid. So it used to be a 0, it's on its way to changing to be a 1. There's a certain point at which it stops being a 0. How long will it be before the output basically goes invalid? So we measured propagation delay as valid in to valid out. What we're going to call the contamination delay, okay, TCD, is a measurement from invalid in to invalid out. Basically, how long the gate keeps its old value even though I've started to change its inputs. You're always allowed to treat TCD as 0. You can say, as soon as you change the inputs, I can assume nothing about the outputs. That's the conservative assumption. The contamination delay is a lower bound on that thing. We'll see in a lecture or two, there'll be one instance where we'll have to be careful about TCD, which is why I'm bringing it up now. So typically, when you buy a logic gate, they will tell you the maximum propagation delay, and mostly data sheets tell you the minimum propagation delay, which is what we're calling the contamination delay. So TPD min on a data sheet is really what we're calling how long does the old value stick around even though I put new inputs. Okay, so the contract that we have is that when I change the input to a logic gate, to a combinational device, I would expect the old value of the output to stick around for a little while, and that's guaranteed to be longer than the contamination delay. There's some amount of time it takes for the gate to make up its mind of what the new value is, but we're guaranteed that if we wait at least the propagation delay, that we'll have the new output value. So these two timing numbers, okay, tell us the timing specifications for the gate. So between the functional specifications, which we often get from a truth table, and these timing specifications, and the digital signaling spec, we actually have all the elements of the static discipline that we needed to build now combinational devices. In fact, we can build very large combinational circuits out of combinational components and use the technique we discussed last time in lecture to write down the the specifications, the static discipline specifications for our new larger synthesized combinational device. Okay, quick, what's TPD of that circuit? I've told you that each of the NAND gates has a TPD of 4 nanoseconds. So what are you thinking about? So how long do I have to wait at most? What's the longest time I would have to wait and for the output to reflect new values on the A, B, and C inputs? So I'm really looking for the longest path through this circuit. So you'll go through and you probably decide that the longest path is that one. It goes through 3 NAND gates, so that the TPD would be 12 nanoseconds. For the contamination delay, what's the shortest time in which if I start changing the inputs here, the output will stay valid? And now we're looking for the shortest path, and then we'll sum up the TCDs along the shortest path, and we'll in this case, get 2 nanoseconds. Okay, so you'll get lots of practice of this with various tutorial problems. Alrighty, I'm going to stop here. We'll talk about leniency in recitation. Bye-bye. Thank you for finding us. Good luck on lab.